Hello students, welcome to today's chemistry class. Today's chemistry class, I'm going to explain you about solutions. Solution is a homogeneous mixture of two or more substances in the same or different physical phases. So the phases can be different. As you tell, in the daily life we keep coming across the solutions. Solution may be it a homogeneous mixture of two or more substances. A solution can be two gases, it can be two solids, two liquids. It can be any way. But the homogeneous mixture is called the gas. So a solution in which relatively the small amount of solute is present, then that is the dilute solution. If large amount of solute is present, then that is concentrated solution. So solution is homogeneous mixture of two or more substances in same or different physical phases. Same or different physical phases. So the substances forming solution is called component of the solution. The substances forming the solution are called components of the solution. On the basis of number of components, a solution can be two component, that is binary solution. And the components of the solution are solute and solvent. Solute is a component which is present in the large quantity, while the other component is known as the one which is in lesser quantity is solute. Now let us see the classification of solutions. Solid solutions, liquid solutions, and gaseous solutions. In the solid solution, the solute is solid and even the solvent is a solid. Example alloys, nichrome, ornamental gold, all this comes under solid solutions. Solute, solid in solid. The second type is liquid solid solutions. Under solid solutions, liquid solid solutions. Hydrated salts, amalgam of the mercury, these are the examples. So the lesser one is a liquid and the larger one is a solid. Next, the other type of solid solution is gases in solids. Solute is gas, solvent is solid. Lesser one is gas, larger one is solvent. So gases dissolved in the mineral. Some of the gases, hydrogen and nickel, so gases that are dissolved in the mineral is an example. Now the second classification of the solid is liquid solutions. Solid is a solute, liquid is a solvent. The you can observe here for the solid solution, the larger component is solid. For the liquid solutions, the larger component is liquid. And for the gaseous solutions, the larger one is gases. Okay, so now in the liquid solutions, solid in liquid, sugar solution, liquid in liquid, alcohol in water, gas in solid, gas in liquid, gases in liquid, gases in liquid, aerated drinks, beverages, soda, all these are examples. Gaseous solutions, for gaseous solutions, solid in gas, iodine vapor in air. For gaseous solutions, the larger one, solvent is gas. Solid in gas, iodine in air, you can take example. Liquid in gas, water vapor in air. Gas in gas, air. Atmospheric gases. Example we can take atmospheric gases. So nitrogen it is 78% and the remaining gases are oxygen, noble gases. So different gases are in the less percentage. So this is the atmospheric gases also come under a solution. That is also a homogeneous mixture. Then that is a homogeneous mixture. Now, if water is the solvent, then that is aqueous solution. If it is not water, non-aqueous solution. If it is water is a solution, then it is aqueous solutions. If water is not, then that is non-aqueous solution. Next, unsaturated solution. What is unsaturated solution? What is saturated solution? Seeing the basics, then we'll go into the actual syllabus. See, after looking on to other basics, we'll see the actual syllabus. So, what is a saturated solution? Solution in which more solute can be dissolved without raising temperature is called unsaturated solution. Is called as the unsaturated solution. And saturated solution is the solution which no solute can be dissolved further at a given temperature is called saturated solution. Next, what is a supersaturated solution? Solution which contains more solute than that is necessary to saturate at given temperature is called supersaturated solution. It is called supersaturated solution. Now, what is solubility? Maximum amount of solute that can be dissolved in a given amount of solvent at given temperature is known as solubility at that temperature. And if solute content is more, than that is concentrated solution. If solute content is less, then that is dilute solution. The maximum amount of the solute that can be dissolved in a given amount of solvent at given temperature is known as solubility at the temperature. Solubility depends upon different factors. Nature of the solute, nature of the solvent, temperature of the solution, pressure. And now we'll see Henry's law. Simple one, Henry's law and its application. Most commonly Henry's law, it is for the gases and liquid solutions. Partial pressure of the gas in vapor phase is proportional to mole fraction of the gas in the solution. And it is expressed as P is equal to KH by into P. Greater than the KH value, higher will be the solubility of the gas. As the value of KH decreases with the temperature, even the solubility will decrease. Okay, so this Henry's law can be applied in different ways. X by here, this the application part of the Henry's law is in manufacture of the soft drinks, soda, carbon dioxide is passed at high pressure to increase its solubility. P is proportional to M or P is proportional to X. Mole fraction of the gas is X. I've told you mass of the gas and partial pressure of the gas. So P is proportional to X. So greater is the KH value, higher will be the solubility. In the manufacture of the soft drinks and the soda water, carbon dioxide is passed at high temperature to increase its solubility. To minimize the painful effects accompanying the decompression of the decompression of the deep sea divers, oxygen diluted with less soluble. So the gas is used as the breathing gas. high altitudes, the partial pressure of oxygen is less than the ground level. So this leads to low concentration of oxygen in the blood for the climbers and causes anoxia. So there also we apply the Henry's law. So higher altitudes, the oxygen is getting lesser than compared to the low. So there is low concentrations of the oxygen in the blood for the climbers, which causes anoxia. There also we apply the Henry's law. So P is proportional to X. So mass mole fraction of the gas is proportional to the partial pressure of the gas, which is in the vapor pressure, which is in the vapor phase. Now we'll see concentration of the solutions, how they can be expressed. What is concentration? Before telling you what is concentration, concentration is nothing but amount of solute in the solution is concentration. Amount of solute in solution is concentration. So concentration of the solution, it is defined as relative amount of solute present in a solution. What is concentration of solution? So what is concentration? The concentration of solute is nothing but amount of the solute in a solution is called as the concentration. On the amount of the solute on the solution, on basis of this one, the solution is of two types: dilute solution, concentrated solution. Next, what are the different methods of expressing? Dilute solution, the solute content is less. For concentrated solution, the solute content is more. Now, methods of expressing concentration of solutions. Percentage by weight, W by W. Amount of the solute present in 100 grams of solution. Weight by weight percent. Weight of the solute in weight of the solution is percentage by weight. And percentage by volume, it is defined as the weight of 0.1 gram solute present in 100 ml of the solution. So amount of the solute in 100 ml of solution. Weight by weight is amount of solute in 100 grams of solution. Amount of the solution 100 ml of the solution. Okay, so this is percentage by volume. Next, what is mole fraction? It is defined as ratio of number of moles of component to the number of moles of total number of moles of the components in a solution. It's called mole fraction. X, mole fraction denoted by X. Ratio of number of moles of one particular component to that of total number of moles of the components is called mole fraction. For a binary solution you'll be having two components, A and B, solute and solvent, A and B. So their moles are Na and Nb. So mole fraction of A will be Xa is equal to Na by Na plus Nb. Xb is equal to Nb by Na plus Nb. Okay. So total of the mole fraction is equal to unity always. It can be any number of the components, but the total number of moles of the component is 1. It will be equal to 1. Xa, Xb, Xc, so on. That will be equal to unity. Now, we'll see ppm. What is ppm? We need to know all these basics in the solution. The parts of the component per million parts. 1 part to that of million parts of the solution. It is widely used when solution is present in the trace quantities. Number of parts of the component, total number of parts of the component, 10 to the power of 6. It is the ppm. What is molarity? It is the number of moles of solute present in 1 liter of the solution. Number of moles of solute present in 1 liter of the solution is molarity. Next, what is molality? Molarity we have seen, weight m, it is denoted by m, mass of the solute. M is equal to W by capital M into 1000 by V in ml. So number of moles of solute in 1 liter of the solution is called molarity. So if it is 1 molar, then that is 1. If when the molarity of the solution is 1 m, it is called molar solution. If it is 0.1 molar solution, it is called decimolar solution. 0.1 molar, it is decimolar solution. If it is 0.5 molar solution, semi-molar solution. It is semi-molar. Okay. So 1m, it is a molar solution. 0.5, it is semi-molar solution. If it is 0.1 m, then that is decimolar solution. Now, molarity is equal to percentage of the mass into density into 10 by molecular weight. Now, you are having a dilution law. All these are applicable for your practical chemistry. You need to know dilution law. M1V1 is equal to M2V2. M1V1 is equal to M2V2. So, reaction between the two reactants, M1V1 by N1 is equal to M2V2 by N2. N1 and N2 are the stoichiometric coefficients and balanced equations. Now, what is molality? Molality, it is the number of moles of solute per kg of the solvent is called molality. Next, molality is equal to mass of the solute in grams into 1000 by molecular weight of solute into mass of the solvent. So molality, it is independent of temperature. Okay. When solvent is used water for 1 molar solution, it is more concentrated than molar solution. Now, what is molarity? Here, molarity, I hope you have understood the difference. It is denoted by small m, and this is molarity is denoted by capital M. And number of moles of solute for 1 liter of the solution. Here, number of moles of solute for 1 kg of the solvent is molarity. Right? Now, fourth way of expressing the concentration of the solutions. Normality. Normality, N. Number of gram equivalents of solute present in 1 liter of solution. Number of gram equivalents of solute present in 1 liter of solution is normality. Normality is equal to number of grams minus equivalent of solute by volume of the solution in 1 liter. It is simply, you can tell number of gram equivalents of solute is equal to mass of solute in grams by equivalent weight. So relationship between normality and molarity. N into equivalent weight is equal to M into molecular weight. So a normal solution can be converted to molar solution using this formula. Normality and molarity relation. N into equivalent weight is equal to M into molecular weight. Here you take number of equivalents of the solute in 1 liter of solution for normality. But for molarity, you take number of moles of the solute in 1 liter of the solution. If two solutions have same solute having volumes and molarities, M1V1 is equal to M2V2 mixed. So the molarity of the resulting solution. And similarly for the normal solutions, M1V1 by M2V2 by V1 by V2. Here the printing is gone. The printing you can see. But I'm telling you, for mixing of the solutions, the molarity having M1 V1 and V2 M2, when they are mixed, what is the total molarity for the resulting solution? M is equal to M1 V1 plus M2 V2 by V1 plus V2. And for similarly for normality also, when two normal solutions N1 V1 are mixed and N2 V2 are mixed, you get the final normality N for the solution as N1 V1 plus N2 V2 by V1 plus V2. Now, To dilute V1 ml of solution having molarity M1, see, we are diluting V1 ml of solution with M1 molarity to M2 and final volume is V2. The volume added is given by this formula. V2 minus V1 is equal to M2 minus M1 minus M2 by M2 into V1. Similarly, V2 minus V1 is equal to N1 minus N2 by N2 into V1. Next, what is formality F? It is the number of formula weight of solute present per liter of the solution. It's called formality. Formality is equal to moles of the substance added to the solution by volume of solution in liter. Now, we'll see the next one. What is mass fraction? Mass fraction of any component in the solution is the mass of that component divided by total mass of solution. Is the mass fraction. Now, molarity, mole fraction, mass fraction are preferred over molarity, normality, etc. because former involves weights which not change with temperature. Okay, molality, mole fraction, and mass fraction are more preferred than molarity and normality because these doesn't change with temperature. So these are the more preferred ones. Now, what is D? D, it represents 1 mole of solute present in 1 liter at 0 degrees DML. What is DML? It is 1 mole of the solute present in 1 liter of the solution at 0 degrees is called DML. So these are the basic terms that are to be known for the practical chemistry as well as for your practicals as well as for your theory part. Now we'll see what is Raoult's law. The Raoult's law states that for a solution of two volatile liquids, the vapor pressure of each liquid in solution is less than the respective vapor pressure of the pure liquids. In the equilibrium partial pressure of the liquid, it is directly proportional to mole fraction. So here, for a solution of two volatile liquids, the vapor pressure of each liquid in solution is less than vapor pressure of pure liquids and equilibrium partial vapor pressure of this liquid. It is directly proportional to the mole fraction. So Pa is proportional to Xa. Pa is equal to K into Xa. Xa is equal to Na by Na plus Nb. This is equal to mole fraction of the liquid A. So for any solution containing two liquids AB, partial vapor pressure of the liquid A, partial vapor pressure of liquid A is Pa. And the mole fraction of that one is Xa. Pa is proportional to Xa. Pa is equal to K into Xa. Xa is nothing but number of moles of A component by total number of moles. Now, in the proportionality, it is considered by pure liquid. Xa is equal to 1, Ka is equal to P naught A, the vapor pressure of the pure liquid. Hence, Pa is equal to P naught A into Xa. Pb is equal to P naught B into Xb. Total vapor pressure of the solution is equal, Pt is equal to Pa plus Pb is equal to P naught A into Xa plus P naught B into Xb. So this is equal to P naught A plus P naught B minus P naught A into Xb. I'm repeating once again Raoult's law. What Raoult's law states is relative lowering. Raoult's law, simple way I'm giving you the definition. Relative lowering of vapor pressure of a dilute solution is equal to mole fraction of that solute present in the solute, present in that solution. Relative lowering of vapor pressure of dilute solution, it is equal to mole fraction of the solute present in the solution. So therefore, P naught minus P by P naught is equal to mole fraction of the solute. P naught minus P by P naught is equal to small n by n plus capital N. Now, later we can see the derivation. What is Noval's law? Noval's law. At any fixed temperature, vapor pressure is always richer in more volatile component compared to the solution phase. In other words, mole fraction of the more volatile component is always greater in vapor phase than in solution phase. Composition of vapor phase in equilibrium with solution is determined by the partial pressure of the components. Yn, Y1 and Y2 are the component 1 and component 2 respectively. Vapor phase then, the Dalton's law of partial pressure P1 is equal to Y1 into P pressure of the total. P2 is equal to Y2 into pressure of the total. Now we'll see what are the ideal solutions. The solutions which follow Raoult's law are called as the ideal solutions. Ideal solutions. The solutions delta H of mixing is equal to 0, delta V of B is equal to 0, and the solutions which obey Raoult's law are the ideal solutions. The solutions in which solute BB, solvent AA interactions are similar to solvent AB. Here, the attraction between the solute, solvent, the solutions in which the solute interactions and solvent interactions, the interactions are almost equal to the total solution formed after mixing solute and solvent. These are called ideal solutions. The forces of attractions between the solvent molecules, solute molecules and solvent molecules, and finally formed solute solvent molecules, the interactions are all same. This is called an ideal solution. Okay, and the second condition for the ideal solution is the ones which obey the Raoult's law are called as the ideal solutions. P naught A is PA is equal to P naught A into XC. PB is equal to P naught B into XB. That is Raoult's law. Solutions which obey Raoult's law is ideal solution. So what is delta H of mixing? The heat before mixing and heat after mixing is almost zero. No energy is involved. Next, volume before mixing and after mixing is almost the same. Okay, so these are called as the ideal solutions. Once if you take the graph here, the forces of attraction are the same. This is the ideal behavior. Here, this is the partial pressure of the B component. This is the partial pressure of the A component. And after mixing, you get the total partial pressure P naught, PT. So you get, this is the ideal behavior. Now, what is non-ideal behavior? We'll see. The solutions which does not obey Raoult's law are non-ideal solutions. The solutions delta H of mixing is not equal to 0. Delta V of mixing is not equal to 0. And the forces of attraction are also not same before mixing and after mixing for solute and solvent molecules. Non-ideal solutions show positive deviations as well as negative deviations. So AB interactions are weak than AA and BB. See, AA is the solvent interaction, BB is the solute interactions. After mixing, you get AB solution, solvent, solute. This is solvent and this is solute. So the interactions between this AB, interactions between this total solutions are weaker than the previous ones, are called as the non-ideal solutions. So which are showing positive deviation. Here, see, the weaker interactions, therefore vapor pressure is more. You see here, and delta mixing is more than 0, delta V of mixing is also more. Heat of reaction and volume of the reactions are more than 0. Okay, so this is the one form. Actually, you have to get a straight line. If this is the ideal behavior, this dotted lines you have to get in this way, that is ideal behavior. But due to weak attractions, more vapor is formed and more vapor pressure, you can see. Okay, so this is the positive deviation. Now, what is negative deviation? Negative deviation is, here you can see, if the AA interactions, BB interactions are stronger, AA interactions and BB interactions observed, and final attractions, whatever you are getting, are stronger than AA and BB. So solvent is AA, solute is BB, and next formed is AB. If these attractions are formed, solution attractions are very strong compared to solvent and solute individual, then here AA, BB interactions, AA interactions and BB interactions. Finally, you get AB interactions. So the formed AB interactions are more strong compared to AA and BB. Therefore, each component of total vapor pressure will be lesser because of strong interactions between the AB. The vapor is not formed, the bond breaking is less, vapor formation is less. So more than the ideal behavior, you get lesser vapor pressure here. These are the dotted lines for the ideal behavior, but you're getting lesser ones. So this is the negative deviation. The last concept of the solutions is azeotropic mixtures. What are azeotropes? A mixture of two liquids which boil at particular temperature, like the pure liquid, and distills over the same composition, just like the boiling mixture with no change in composition, is called azeotropic mixture. The azeotropes here for the non-ideal solutions, you can see azeotropic mixtures. Mixture of two or liquids, they boil. Mixture of two liquids which boil at particular temperature, like pure liquid, and distill over in the same composition with no change in the composition, is known as constant boiling mixtures. And in these, you are having minimum and maximum. So the azeotropic mixtures that distill, the non-ideal solutions which show positive deviations from Raoult's law, come under this category, minimum boiling azeotropes. If they boil lower than the boiling temperature of the two components, then they are called as the minimum boiling azeotropes. The ideal, non-ideal solutions showing positive deviations are minimum boiling azeotropes. The ones which distill lower than the boiling temperature of the two components is minimum boiling temperatures. And the mixtures which boil above the boiling temperature of the individual components, the mixture which boils at more temperature than that of individual components, is maximum boiling temperatures. Maximum boiling azeotropes. So generally non-ideal solutions with negative deviations are called as the maximum boiling azeotropes. So I hope everybody have understood. I'm repeating, the mixture of two liquids which boil at one particular temperature of the pure liquid and distills in the same composition with no change in the composition. Both of them after mixing, they boil at the same temperature, but there is no change in the composition, called as azeotropes. So non-ideal solution having positive deviation are minimum boiling azeotropes. And the next one is the azeotropes The non-ideal solutions showing negative deviations are called maximum boiling isotopes. So minimum boiling isotopes are the liquids which boil to the lesser temperature than that of boiling temperature of the individual components. And maximum boiling isotopes are the mixtures where the mixture will boil at a boiling temperature which is more than the boiling temperature of individual components, are called as the maximum boiling isotopes. For minimum boiling isotopes, ethanol, you can take example with water. And the next one is HCl and water. These are the examples. I hope everybody have understood this class. What we have discussed is about the solutions. What are solutions? Types of solutions, and what are the basic terms involved in the solutions, and what are the different types of expressing concentrations, how you express the concentrations, Henry's law, Raoult's law, concentration, their formulas, Henry's law, Raoult's law, and what is ideal solution and deviations of the ideal solutions. Thank you everybody for listening to my class.